Welcome to the video lecture series for Texas A&M University course Math 150. Today we will look at section 1.7 Transformations. You can find the accompanying handouts at bit.ly/RayleneMath150. Let's begin. Now that we have looked at the library of parent functions and we know what the untransformed or the basic functions look like, we can get all sorts of other graphs almost for free simply by applying a consistent set of rules to these basic graphs. These rules are reflections, scales, and translations. In doing these things, we have a predictable way of changing each graph, no matter how it started out looking, to get a result. So applying a certain kind of transformation to the square root graph or to the reciprocal graph will result in the same kind of change no matter where we started. Anything that we do to the x value is called a horizontal transformation or horizontal change. Anything that we do to the y value is called a vertical change or a vertical transformation. There are two types of transformations to consider: rigid transformations or non-rigid transformations. Translations, or shifts as the textbook refers to them, and reflections are called rigid transformations because they do not change the size or shape of the original graph. Meanwhile, a scale, which is a shrinking or a stretching of the graph, is a non-rigid transformation. That's because scales change the size or shape of the original graph. All right, well, let's take a look at each of the three types of transformations: reflections, scales, and transformations, one by one. Each of these we will look at to see how it affects x and how it affects y. In other words, we will look at horizontal reflections and then vertical reflections. We will look at horizontal scales and then vertical scales. And lastly, we will look at horizontal translations and vertical translations. But first, let's take a look to see what happens if we need to come up with a basic function or a parent function. So let's go back to our creating the graph from a table of values. For the explorations of the transformations, we are going to consider the same parent function each time, y equals the square root of x. Let's create a table of values. We have a domain restriction that the radicand of even roots must be greater than or equal to 0. In this case, the radicand is simply x. So we know that x must be greater than or equal to 0. So any x value that is negative under the square root produces a non-real y value. We will talk later about the difference between non-real and undefined or indeterminate y values. But for now, we will just write the word non-real in here. Because y is not defined, we know that the x values that make y not defined are not in the domain. So we don't really need to consider anything that happens to the left of the y-axis, because to the left of the y-axis is when x is less than 0. When x is 0, the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2. It is not plus or minus 2. There is only one output for a function. The square root of 9 is 3, and the square root of 16 is 4. So with these ordered pairs, we can plot some points and get a sense of the graph. And so our graph looks like this. We can see then that the graph for y equals square root of x has a domain of x greater than or equal to 0, and it also happens that the y values are never negative, because the square root of a value is the non-negative result. So the graph doesn't lie down here either. So the range is y greater than or equal to 0. Now that we have the basic graph, we're going to see how we can apply these reflections, scales, and translations, known collectively as transformations or changes, to this basic function. So with reflections, what we need to know numerically about a reflection is that it changes the sign of a coordinate. Graphically, we are reflecting through an axis, either the x-axis or the y-axis. So we're going to consider each of these transformations from the perspective of the rule of 4: verbal, numerical, algebraic, and graphical. Horizontally reflect through the line x equal to 0, also known as the y-axis, in order to get a horizontal reflection. So if I take a point here, located at a comma b, and I reflect it through the y-axis, or the line x equals 0, I change the sign of the x-coordinate. So horizontally reflect by doing what? We multiply. So we multiply, or by multiplying every x-coordinate by -1. So this is the verbal description. Numerically, we are not going to change the sign of y, we are going to change the sign of x. So there's no need to talk about, what we're going to do is take the sign of every x-coordinate and change it. So horizontal reflection takes a -9 to a +9, takes -4 to +4, takes -1 to +1, and takes 0 to 0, -1 to -1, +4 to -4, and +9 to -9. So even though we started off with an x value of -9, it's going to behave like +9. So using the square root notation, what we're going to have is y equals the square root of x, but upon changing the sign of x, this turns into y equals the square root of -x. The function notation says that the parent function is y equals f of x, but the horizontal reflection says to multiply x by -1. So y equals f of -x. So what's happening here in the table of values is that we really want to consider x, changing the sign of x, and then y. So normally we would have a table of values with some different inputs for x. Normally when x is -9, y is non-real. But before we get to the y-coordinate, we have to change the sign of x. So the new x-coordinates become 9, 4, 1, 0, -1, -4, -9. And then in order to take this x-coordinate, or this new x-coordinate, and get the y value, we take the square root of the new x-coordinate. So the square root of 9 is 3, then 2, 1, 0, and then these are all non-real. So whereas the graph of the original used to be in red, like this, the new graph with the blue ordered pairs will look like this. -9, 3, -9, 3, -4, 2, -1, 1, and when x is, and 0, 0 still, but when x is +1, we would get a non-real result. So the graph has been horizontally reflected to look like this. So the blue is the graph of y equals the square root of -x. We don't really need to make a table of values if we understand how to take the parent function and what this algebraic notation is telling us to do. It's telling us to take each point and reflect across the y-axis. Take a look at what happens with vertical reflections. This would be a good time to pause the video, try completing this page on your own, and then compare with my explanation. A vertical reflection is still a reflection, so we still multiply by -1. But because y is the vertical coordinate, we are now multiplying the y-coordinate by -1. And if we were multiplying the y-coordinate by -1, we are changing negative y's into positive y's. This is the region where y is negative. This is the region where y is positive. And we are going through the boundary from negative to positive when y is 0. Y is equal to 0 on the x-axis. And therefore, a vertical reflection goes from bottom to top, or top to bottom, by reflecting through the line y equals 0, which is also known as the x-axis. We do this by multiplying every y coordinate, because y is the vertical coordinate, we multiply by -1. So in this case, y has no value, so we still have no value, non-real. And all of these values are non-real. Then we take the y coordinate of 0 and multiply by -1 to get 0. This y coordinate changes sign, changes sign, changes sign. Using the square root notation, the original graph or equation of y equals square root of x becomes -y equals square root of x, because we are changing the sign of y. We can take that one step further and rewrite it as y equals negative the square root of x. It's important now to compare with the previous slide where we had negative square root of negative x. The negative was inside the square root for a horizontal reflection, whereas now the negative is outside of the square root. For this reason, that it's easy to confuse the negative outside with inside, I prefer this version of the equation, because it's clear that the negative affects y and not x. In the function notation, we have y equals f of x. Multiplying y by -1 gives us -y equals f of x. This is going to be the general term or expression for vertical reflection, because what is happening is the y is being multiplied by -1, a vertical reflection. So we can still plot our original curve. I used the red for the original before. I will continue to use red for the original curve. And you should be getting very fast at the ordered pairs. So this is the original curve, y equals the square root of x. Now what we are going to do to get the new curve in blue is to take all of the y coordinates and multiply by -1. So that point's the same. This point goes down 1, this point goes down 2, down 3, and down 4. Notice that we are not changing the x coordinates, we are only multiplying the y coordinate by -1. And the blue graph is our new curve, y equals negative the square root of x. Or, as I said, I prefer -y equals the square root of x. Okay, moving on, we're going to take a look at the second of 3 types of transformations, scaling. And just to give you an example of scaling, let's take a look at a Word document. And on a Word document, let's draw a rectangle or some kind of, let's see here, a rectangle or some kind of shape. It's taking a moment to open up a new document. And here we go. So we go to the drawing menu. And let's draw a rectangle. If I take that rectangle and hold the Shift key, then I can drag it and resize it. The resizing is keeping the width and the length in proportion. And this is what we want to do by scaling. If I want to scale horizontally, then I'm only going to resize the x length. If I want to resize vertically, or scale vertically, I'm going to multiply the y. And if I want to keep proportions, I hold the Shift key and I rescale like this. So scaling is a changing of the size and maybe the shape. For example, if I had a circle, oh, where did my circle go? If I hold the Shift key as I draw it, I get a circle in proportion. But then if I scale only horizontally, the circle turns into an ellipse. Okay, let's go back to scales. In the case of a scale then, we are going to multiply either the x-coordinate or the y-coordinate by a constant. We will consider this constant to be positive because if it is a negative that we are multiplying by, that means that we had a reflection. We've already discussed that. So verbally speaking, if we apply a horizontal scale factor of 1/2, what we are doing is multiplying every x-coordinate, multiplying every x, because x is horizontal, by a certain number. It sounds then that we are multiplying the x-coordinate by 1/2. If we multiply the x-coordinate by 1/2, then each of these x-coordinates become the new x-coordinates of -9/2, -4/2, -1/2, 0/2, 1/2, 2, and 9/2. Using square root notation, we would expect then that y is equal to the square root of 1/2 times x. But let's just see what happens graphically with the graphing program if we actually take the equation and multiply 1/2 by x. So here's our parent function, y equals the square root, if I can get this right, the square root of x. Okay, we should recognize the ordered pairs easily enough. And let's focus on the point that makes the height 2. We don't want the height to change. We want to take this x-coordinate of 4 and multiply it by 1/2, which means that that x-coordinate should become 2. So we should be getting the point 2, 2 on the new graph. All right, so basically you want to imagine squeezing this graph inwards, and all the other points are going to be squeezed to half the width. The x-coordinate, for example, here is 0, and so when we squeeze it, it's actually going to stay fixed, because 0 times 1/2 is still 0. Okay, well let's put in what we think is the new equation, the one that we've just written here, because we're multiplying x by 1/2. We would have the square root of 1/2 x. And when we look at that, the point over here has gone all the way over here, from the point 4, 2 to the point 8, 2. What has happened to the x-coordinate if 4 goes to 8? We've multiplied by 2, but we wanted to multiply by 1/2. So maybe this isn't the correct equation to represent a horizontal scale of 1/2. Since it did the opposite, let's try a different number in here. The opposite of multiplying by 1/2 is multiplying by 2. What happens to the point 4, 2 now? The point 4, 2 goes to the point 2, 2. So our x-coordinate that was 4 has been multiplied by 1/2 to get an x-coordinate of 2. So back over here we see that this is actually not correct. It seems logical, but if we want to have a horizontal scale factor of 1/2, we need to multiply by 2 inside the square root. I'll take a look numerically why in class. The function notation then says that y is equal to the function f, which is the square root here. And let's just highlight that to see. The square root is the same as the function, and the function is of 2x. So although it seems illogical, every time you see this, you are to state that we have a horizontal scale of 1/2, not of 2. All right, let's go back to drawing our original graph. When x is 4, y is 2, when x is 9, y is 3, 16, 4. There is the original function, which is y equals the square root of x. We are now going to horizontally scale every x-coordinate by 1/2. So for each ordered pair, the x-coordinate gets multiplied by 1/2. That's kind of tight in there. That's 1/2, 0. This point of this is 1/2, 1. This was 4, 2. 4, 2 becomes 2, 2, which is the point we saw in the graph window. This is the point 9/2, 3. Again, I'm sorry, in red it is the point 9, 3. It becomes 9/2, 3. 9/2 is 4.5. So it's like we are squeezing the graph that way by a factor of 1/2. And lastly, this point was the point 16, 4. Half of the x-coordinate of 16 is 8, 4. And the graph looks like this. It's a little hard on such a small grid to see the difference, so let's go back to the graphing program to compare. This is a much nicer view of that same picture. I'll just turn off the horizontal line. Okay, and we'll take a screen snapshot of this graph so that we can see it a little bit more accurately, and we'll add it to the lecture notes. Okay, so the blue graph is the transformed graph. The red graph is the parent function, y equals square root of x. Do you remember what the blue graph's equation is? For a horizontal scale of 1/2, y is equal to the square root of 2x. So do be careful of that change. Now would be a good time to pause the video and to give yourself a chance to apply what we just saw to a new situation of the vertical scale. The connection is that we're still scaling, so we're still multiplying by a positive quantity, but because it's a vertical scale, this time we are multiplying the y-coordinate. So feel free to pause, fill in the table, and unpause when you're finished. Okay, I'm going to go through this a little bit more quickly. Apply a vertical scale factor of, well, let's just go and see. It looks vertical scale means we are multiplying y, and it looks like every single time we have multiplied y by 2. So fill in 2. Apply a vertical scale of a factor of 2 by multiplying we do it to y coordinate by 2. So using the square root notation, we're doing something to y. Again, we would think it's 2y is equal to the square root of x. But that's probably not what is consistent with what we just saw. So I'm going to second guess it and think we multiply by a half times y in the equation, which has the result of doubling the y-coordinate. Let's just take a look at a graph to compare. Well, let's change all of these. Here again is our parent function, and let's focus on what happens at the point 4, 2. Okay, we want to double the y-coordinate. We want to scale it by 2, so we want this y-coordinate of 2 to go to a y-coordinate of 4. We're not changing the x-coordinate. We now think, because we've made a connection, that the equation should be 1/2 y is equal to the square root of x. And we see that the point 4, 2 on the parent function has become same x-coordinate of 4, but double the y-coordinate, from a height of 2 to a height of 4. And so it worked. Some of you may think, that doesn't make sense, I've not done transformations like that. That's because we're very used to solving for the y, and if we solve for y, we end up getting that y is equal to 2 times the square root of x. This may be how you're used to seeing it. My preference is to put the 2 on the same side as the variable it affects, and then we will always do the opposite of what the transformation says. Again, I'll review this again in class. So we've got our transformation like this, and the function notation says 1/2 y is equal to f of x. Or if you prefer, y is equal to 2 times f of x. Our parent function in red has some familiar ordered pairs. And every y-coordinate will be doubled. So we take each y-coordinate and double it, point by point. So a y-coordinate of 2 becomes 4, a y-coordinate of 3 becomes 6, and a y-coordinate of 4 becomes 5, 6, 7, 8. And so the scaling or the stretching this way is a vertical scale, as opposed to the last one, which was a horizontal scaling. Now you may notice that I've been forgetting to put in the domain and range each time. Please do complete that in the handout, and in the completed lecture notes I will go back and fill it in. Okay, let's move on and try the last of the 3 transformations. This one is often known as a shift, but I'm going to call it a translation. The reason for that is that our transformations will be R for reflection, S for scale, and a different letter, T for translation, as opposed to S for shift. The alphabetical order will be helpful in finding the order that we apply transformations. A translation is an addition or subtraction. So let's review. A reflection is multiplication by -1. A scale is multiplication by a positive constant, different from 1. And a translation is adding or subtracting. So graphical transformations of a parent function are nothing more than multiplying and adding when we think numerically. Okay, apply a horizontal translation of how much to the what by adding -3. Well, if we're applying a horizontal translation by adding -3, it's a horizontal translation of 3 spaces, but to the left. The negative is a direction, and since it's horizontal, our options are right or left. Or instead of adding negative 3, we can consider we are subtracting 3, and we're doing it to the x, because x is horizontal. So for every x coordinate, we are going to subtract 3. So we get negative 12, negative 7, negative 4, negative 3, negative 2, 1, and 6. Well, using square root notation, we know that we're going to do something to x. And it looks like we are subtracting 3 from every x coordinate. So maybe this is what works. Again, let's confirm our conjecture or educated guess in the graphing program. So here's our basic function. Let's center the grid a little bit more. We want every x coordinate to move left 3 spaces. So we think that the new graph will have the equation y equals the square root of x minus 3. Which direction did the red graph move to get to the blue graph? It went 3 spaces to the right. Well, that's unfortunate, but fixable. We want to go in the opposite direction, so we're going to change this to x plus 3. And now the red graph has moved left 3 spaces. Let's consider the point 4, 2. That point has moved 1, 2, 3, oh, I can't see it very well, 1, 2, 3 spaces. 1, 2, 3 spaces to here. And it does in fact look like the point has moved 3 spaces. So maybe you didn't really believe that. Let's try this. In the red graph we had the point 4, 2, and in the blue graph we would have the point 3 spaces to the left is going to be 1, 2. We're not changing the y. Now can you count the spaces better? 1, 2, 3. So each point for the same height has moved left 3 spaces. Right. This is not correct. But it's kind of consistent with what we saw in the horizontal and vertical scales. To the variable, we do the opposite of the instructions. Again, I'll explain why numerically in class. But we get y equals the square root of x plus 3. So for a general function, not just the square root function, a horizontal scale, a horizontal translation of 3 to the left would look like y equals f of x plus 3. The parent function, we should be able to do this in our sleep now. Looks like this. Y equals the square root of x. And the transformed or new function, which we don't have to make a table of values for anymore. We just take each of the original points and we subtract 3 from the x-coordinate, or we move it 3 spaces to the left. 1, 2, 3, 1, 2, 3. There's the point from the graphing window. 1, 2, 3, 1, 2, 3. And we try to draw accurately. It looks like the graphs are going to run into each other. Don't worry. Don't forget to complete the domain and range. Now is a good time to pause the video so that you can give the vertical translation case a try on your own. This time, the translation is being applied to y, so we are going to add or subtract to the y coordinate. According to the table of values, we see that the original y in each case has been decreased by 3. So decreasing by 3 is subtracting 3, and the y coordinates are moving down 3 spaces. So apply a vertical translation of 3 spaces down by subtracting 3 or adding negative 3. It's up to you. I'm going to say adding negative 3 to every y coordinate because y is vertical. Using the square root notation, I would be inclined to think that it's y minus 3 equal to square root of x, but I'm thinking that it has to be the opposite in order to get the change I want. So I'm going to test my conjecture in the graph screen. So we have the graph, parent graph y equals the square root of x. I want each point on the graph to go down 3. I'm just going to plot a sample point in red. Interesting. Of 4, 2. If that point goes down 3 spaces, it should land at 4, -1. So we want to change the y on the new function. We thought it should be y minus 3, makes sense, but we're learning that we have to do the opposite. And in this case, we see that that point, when x is 4, has a y-coordinate that is 3 spaces less, at 4, negative 1. All right, we're getting the hang of this. Okay, so let's take a look at the function notation. Y plus 3 is equal to f of x, or if we wanted to isolate for y equals f of x minus 3. Plotting the parent function in our sleep gives us this graph. And taking every y-coordinate and subtracting 3 or adding negative 3 takes us here. This is a height of 4, so this goes to a height of 1. Apologies, that's a height of 3, so it takes us to the x-intercept. This is a height of 4, taking us down 3 to a height of 1. And we have the graph of y plus 3 equals the square root of x, or y equals the square root of x minus 3. Be careful that we don't slip the negative 3 inside so that we're changing what numerically and algebraically is a vertical change to a horizontal change being done to x. This is one of the reasons I don't prefer this notation, and I prefer this one because it's very clear that the change is happening to y, and it doesn't get unclear that it's happening to x. This green is incorrect, but the blue is actually fine. We just want to be careful where the square root sign ends. For that reason, we could also express the blue as y equals negative 3 plus x. Okay, I want to do one example on the order of applying the transformations, but I think we've had quite a lot for now. I'm going to leave you to try exercise 1 on your own, rather exercise 2 on your own, and then nope, I still mean exercise 1 on your own. And then we'll come back and do the rest in the problem-solving session. Please make sure that you've completed the handout and prepared a list of clarifying questions about the lecture. That's all for now.